Welcome everybody. Today we are very excited to have Barak Gerboz presenting their ICML 2022 paper, NISPA, Neuro-Inspired Stability-Plasticity Adaptation for Continual Learning in Sparse Networks. Barak is a machine learning PhD student at the Georgia Institute of Technology, and he's been working on neuro-inspired continual learning. So we're very excited to hear more about this paper and the sparsity approach here, Barak. So without further ado, please take it away.
Thanks, James, and thank you for the invite. I am very excited to be here and talk about our recent work. So as James said, I will be talking about our recent work, NISPA, Neuro-Inspired Stability-Plasticity Adaptation for Continual Learning in Sparse Networks. This is a joint work between my advisor, Konstantin Dollars. First, I will describe some of the biological aspects of continual learning. Then I will briefly talk about some of the related work. Then I will continue by discussing details of our method NISPA. Then I will share some experimental results, and I will finish my talk with some conclusions and future work. I know that audience is familiar with continual learning, but I will just briefly summarize some of the terminology. So artificial neural networks achieve pretty good performance across large variety of tasks, but they primarily rely on fixed datasets and stationary environments. So in continual learning, however, we have sequential tasks that change in time. So the environment is dynamic. Under such a continual learning scenario, models forget previously learned information once they are introduced with a new knowledge. So this is the problem we call catastrophic forgetting, and it is one of the main challenges of continual learning. So artificial neural networks lack a critical characteristic of a general intelligence, which is sequential learning more and more information over time. In contrast, the brain excels in continual learning, and it offers the only existing proof we know that efficient continual learning is possible. Motivated by this observation, we study 4 mechanisms of the brain that we think are relevant for continual learning and that can be adapted to design of deep learning models. So our first observation is that biological neural networks are sparsely connected. Now I will give you some examples from smaller creatures. They are unique because we have access to wiring diagrams of these creatures in the neuron level. So we have a very detailed map of their biological networks. So first creature is like C. elegans, which is a tiny nematode. And we know that its whole neural network has density less than 4%. Second, we have the Drosophila or fruit fly. We have the full map of the optic medulla of this fly, and its density is only 6%. On the other hand, more complex brains, such as the mammalian brains, are also sparse. For example, here I show you a plot of synaptic density of the human brain. And please note that unless I indicate otherwise, I will be talking about the mammalian brain for the rest of the presentation because some of the observation may change depending on the type of the brain. But I will be talking about the mammalian brain for the rest of the talk. So initially, our brains are sparse at birth. Then we have this phase after birth where we observe significant synapse formation. So during this period, our brain becomes denser. And in early childhood, density of the brain peaks, which is around when a child is 6 years old. After this peak, we observe a synaptic pruning driven by learning. So this is a very crucial stage because during this period, novel experiences directly affect the way the brain is wired. After this pruning phase, brain becomes sparse again. And for the rest of the life, we observe relatively constant sparsity levels in healthy adults. So the take-home message is that our brains are sparsely connected, and this sparsity is relatively fixed for the most of the duration of life. So we have persistent sparsity that doesn't change much. So in contrast to their biological counterparts, artificial neural networks have densely connected layers. This is very obvious for fully connected layers, but maybe one may argue that whether convolutional layers are sparse or dense because there is some sort of weight sharing. But conceptually, convolutional units operate on all the future maps of previous layers, so they are still conceptually dense because of the computation they perform. Second observation is that mammalian brain has dynamic topology. It learns through two mechanisms. First, functional plasticity, which adjusts synaptic transmission rates. Second, we also have structural plasticity, which rewires the connections in order to create novel neural pathways. In contrast, artificial neural networks have static topology. They only have weight updates. This can be considered as similar to functional plasticity in the brain, but due to dense connectivity, there is no room for rewiring or structured plasticity in artificial neural networks. Next, our third observation is that the brain has selective plasticity. So some connections are dedicated to remembering old experiences, while others are dedicated to learning new information. First part of the selective plasticity mechanism is that brain forms new connections while learning new tasks. Here I will show an experimental result on mice. So first, researchers put mice in a scenario in which mice require learning new skills. Then they study how pyramidal neurons in the mouse cortex responds to this novel learning episode. So here we observe that this novel experience triggers some formation of new spines. And here we have more quantitative result, which compares this learning-driven formation with a control case. As you can see, exposure to new experiences triggers more spine formation. And these figures show how this process unfolds in time. So first, while learning, the brain forms new spines. However, only a tiny fraction of these new connections survive the first few weeks after learning. So most of them are pruned, but we have some survived novel connections. And these survived connections are stably maintained later in life to remember the associated skill. So this indicates that learning leaves small but permanent mark in the brain connectivity, and these permanent marks are stable, or like similar to freezing mechanism in the deep learning domain. So to sum up, in the brain we have task-specific connections that are required for remembering tasks, like previous tasks, and I show them with these colorful dots. On the other hand, we also have plastic connections that can learn new information, and they are indicated by these gray dots. In contrast, artificial neural networks does not have such selective plasticity mechanism by default. We apply all weights the same learning rate, so all weights are equally plastic, which means that there is no stability to remember old skills, and that's why deep learning models either require revisiting old tasks or new information overrides the previously learned information, which leads to catastrophic forgetting. And finally, our fourth observation is that the mammalian brain can learn more and more tasks with fixed number of neurons. We know that there is neurogenesis in the brain, but it is neurogenesis, by the way, means creation of new units or neurons. But most people argue that it is not one of the primary mechanisms of learning. In contrast, it's a common practice in deep learning, and like we add new modules or like new set of units if our models need to learn more than one task. So it is very common in deep learning that we have some kind of network growth, and it seems to be not happening in the brain very often. So these 4 points conclude our neuro-inspiration or biological aspects that we want to apply in our solution. Now I will briefly describe some of the related work and how they incorporate some of these observations. So first family of approaches is called regularization approaches. They are simple. We basically assign an importance score for each weight, and we want to somehow protect them. So we penalize the change of these weights. Second type of method is architectural methods, and I divide them into two subcategories, which is expanding network category. These type of methods dynamically allocate new neurons for new tasks, and we have fixed capacity or fixed network size architecture methods, and they try to distribute available resources across multiple tasks in a smart manner. And finally, we have replay methods. These methods store or generate samples that belong to previous tasks, and they frequently mix it with the new training dataset in order to avoid forgetting. I should admit that these methods are the most powerful one, but they come with significant overhead, and for some applications, some form of replay is not possible. We also know that brain employs replay, but most of the proposed approaches are biologically implausible. Of course, there is also biologically plausible replay mechanisms, but I will not go into details because our method focuses on regularization or architecture changes. But replay is also a very important part of continual learning, and I think we can use it in like future works. So basically, I will summarize give like few examples of existing works. For example, in terms of regularization methods, memory-aware synapse is one of the most famous one. Here we assign an importance score for each weight, and it determines the plasticity of the corresponding weight. So like the brain, regularization methods have selective plasticity, and they can learn multiple tasks without adding new modules to the network. However, they have fixed density, like they have dense topology. This makes connections highly entangled, which means even slight change in weights affect all the other units. And that's why small changes accumulate throughout the network if we use regularization, and models still suffer from forgetting in long task sequences. Second, I will talk about the expanding network method. Maybe this is the most extreme case of expanding network methods. So I will talk about progressive neural networks. Here, this is the extreme case because we freeze the whole network after learning a task. Then we horizontally add a subnetwork that is connected to frozen body. Here we have some kind of selective plasticity because some of the parts of the overall network is frozen and it can preserve the previous knowledge. And we have dynamic topology because we grow new parts in the network. But the problem is that it comes with huge overhead, which is training cost and inference cost increases linearly with every task. So this type of approaches quickly becomes interactable. Finally, I will talk about continual learning via neural pruning, or CLMP. It's a good example of an architecture method with fixed network size. So here, first we select important neurons for a task. Then we isolate these important units by removing some connections. So we extract some kind of isolated subnetwork. Then we freeze the connections of this isolated subnetwork. Here we have some kind of selective plasticity again, because some parts of the networks are stably maintained and it can learn without growing the network. So it smartly distributes available resources across different tasks. But one problem is that this method comes with dense connectivity, which makes isolation very challenging because we need to drop many connections. Second, this dropping of connection is actually corresponds to pruning network after training. So this causes some performance loss. And finally, this CLMP method quickly runs out of capacity to learn future tasks, because in order to isolate the previous part, we freeze and we drop lots of connections. So we take huge portion of the capacity to store the previously learned information in the subnetworks. Now I will describe our method, NISPA, which combines 4 principles that we previously discussed. So first, like the brain, NISPA uses sparse networks with fixed density to mitigate forgetting. Second, NISPA dynamically changes its network topology when learning a new task. Third, similar to selective plasticity in the brain, NISPA freezes specific important connections to retain previously learned information. And finally, like the mammalian brain, NISPA can learn more and more tasks over time with fixed number of units. So to summarize, NISPA sequentially learns multiple tasks. It does not need to revisit all the examples to remember them, so we do not employ any form of replay or rehearsal. Third, it can accumulate more information into fixed number of neurons, so we do not employ any kind of network growth as well. So NISPA can be considered as either a regularization method or architecture method with fixed network size. So we start by dividing all units into 3 categories. First, we have the plastic units. They learn the future tasks, so they are kind of reserved learning capacity of our method for future. Second, we have stable units. They preserve the learned information and they serve as a memory for our method. And finally, we have candidate stable units, and they are a transition state between plastic and stable units, and they are also responsible for learning the current task. Here is the transition diagram for these 3 states. First, plastic unit can become candidate stable unit or vice versa. These transitions are driven by activations of units. Second, we have a second transition from candidate stable unit to stable unit. And this may only happen at the end of a task. And stable unit is kind of a terminal state of this transition diagram. So once you become stable, you never become plastic or candidate stable again. This also highlights some removal of highly active units has detrimental effect on the overall performance. So this means there's a strong correlation between activations of units and importance for a task. Another concern may be whether too many units will be selected as stable. This will definitely not leave enough plastic units for future tasks. So our observation is that using ReLU activation leads to highly skewed per layer activation distribution. So this phenomenon looks like this. also this is an example on EMNIST, but same observation applies to more complex data sets as well. So as you can see, here we see the distribution of activations, and most of the activations cluster on the left side, which means they have small activation. But on the right tail, we have few units with significantly more activation. So this suggests that we can preserve most of the activation in the network by selecting only subset of units. So we will still have many plastic units for future tasks. Another important point is that this skewness is enforced by ReLU. And this skewness exists even in the first epoch, and the distribution stays skewed throughout the training, which means we can use this intuition at any particular time in the training. So the next question is that when we make this selection or transitions between states, and we solve this problem by dividing a single task learning into multiple phases. So each phase consists of few epochs, and for a single task, we have multiple phases within a task. And we select candidate stable units, or we transition some of the plastic units to candidate stable unit state before each phase. Algorithmically, we follow two simple steps. The first, we compute the total activation for all training samples at each layer. Then we find the smallest set of units that capture at least a fraction tau of layer activation. Here we vary tau dynamically, and it serves as a dynamic threshold for selection. So we schedule these tau values based on cosine scheduling function, and our motivation is to select many units as candidate in early phases. Then we restrict the selection more as we progress into later phases. So intuition is that we want to keep tau high at the beginning because we want to give all units a chance to become stable. But as training proceeds, activations become more stable and units become more competent for the task. And that's why we can restrict the selection process more. So towards the end, we only select few stable units. So after this selection step, we have the connection rewiring. So first, this rewiring consists of connection dropping and growing. First, we drop all connections from plastic units to candidate stable units. So this guarantees that change in the plastic units do not affect the candidate stable units. Another thing is that this candidate stable units only receive from candidate stable units or stable units. So we try to form this kind of isolation from plastic units. However, candidate stable units can still share knowledge through outgoing connection. For example, this unit actually sends some information to the plastic unit. So there is some knowledge transfer going on. It is not total isolation. Another way to interpret this is that dropping forms some input-output paths that never passes through plastic units. So we extract or construct some subnetwork embedded in the overall architecture, which consists of stable or candidate stable units. And at the end of the task, we will dedicate the subnetwork to the current task. So next, we grow connection for every connection we dropped. So this preserves the layer-wise density, which in turn preserves the density of the overall network. So we have two options for connection growth. The first one is between two plastic units. This type of connection promotes knowledge learning new representations because Basically, plastic units have free capacity of learning, and we just form a path between more plastic units. Second type of connection is from candidate stable to plastic unit, or stable to plastic in general. This type of connection promotes some kind of reuse of existing knowledge. We haven't optimized our choice, so we randomly select between these two type of connections. Maybe we can do something smarter about it, and I will revisit this in the conclusions, but here we do not make any difference between both type of connection, and we just randomly select. So in each task, we perform multiple selection and rewiring cycles. Once the task ends, the final set of candidate units becomes stable. Here, our motivation is to form a stable structure embedded in the network that will serve as a lifelong memory for the associated skill. This is similar to stable spines in the mammalian brain, as I explained in this mice experiment. So recall that we are enforcing smaller tau as training proceeds, and we have this skewness observation in distribution. If we combine these two, it means that we select only few stable units at the end of a task. And this also means that we have many plastic units reserved for future tasks. After promoting this candidate stable units to stable units, we freeze the connections between stable units. This guarantees that this frozen extracted substructure in the network will not affected by backpropagation, because they can still receive some ground runs from top-down connection that comes from plastic units. But with freezing, we avoid this problem. So here I will show how this all steps unfolds in time. So we first divide each task training into multiple phases. Initially, we start with a randomly pruned network. So we are sparse at the initialization, but the topology is just random. So before each phase, we select candidate stable units. And at the initial phases, we select many candidate stable units because the tau value is high. As training proceeds, tau value becomes smaller, and we select fewer units. And all selection is always followed by connection rewiring. And this selection rewiring cycle repeats multiple times until phases start decreasing the performance. So we can interpret this operation is that we are performing early stopping in the phase level instead of epoch level. So we track validation accuracy for the current task, and we compute this operation at the end of each phase. Once the task ends, we promote final set of candidate stable units to stable units, and we freeze the connections between them. And we repeat the same process for the second task, but note that we carry stable units with us to second task because it serves as they serve as a memory for our method. Now I will briefly summarize some of our experimental results. I will not go into details of scenario because I know that everybody is familiar with common benchmarks, but one important point is that we are doing task incremental learning, which means that we provide task identifiers even during testing. So this is one of the limitations of NISPA. In the paper, we have some class incremental experiments, but I will not go into detail because they are not the original version of our algorithm. The original NISPA is designed for task incremental learning. So first, we start with a control experiment. Suppose our network has P parameters and T tasks to learn. Then we have two natural control baselines. The first one is single task learner with P parameters. We call it STL. and it serves as an upper bound for our method because it corresponds to dedicating all parameters to a single task. So we do not reserve any of the parameters for future tasks, and we use all learning capacity for the single task, and this is the upper bound. The lower bound is single task learner with P over T parameters. We call it STL ISO. This is a lower bound because it corresponds to partitioning network into T equal sized isolated networks. So any reasonable approach in task incremental scenario should beat this model because it's a very naive approach and there is no transfer of knowledge going on between tasks. And here we see that NISPA significantly outperforms STL ISO, which is the lower bound, and it nearly reaches the performance of STL. So this suggests that NISPA's success is not only due to isolation of connections, but knowledge sharing via novel connections is also a crucial part of the success. Another observation is that we see that accuracy gap between STL, which is upper bound, and NISPA increases as we see more tasks. So this is some kind of limitation of NISPA, and the main problem is that we never unfreeze or we never go from stable to plastic unit or anything in between. So our number of plastic units decrease in time. This is not a problem for earlier layers, but the problem is that you can't basically reuse the existing knowledge at the upper layers of the architecture. So if we have many tasks, NISPA eventually runs out of learning capacity at later layers. That's why we see this increase in the accuracy gap compared to upper bound. Next, we compare NISPA with some of the existing methods. We use 3 regularization baselines and 1 architectural baseline with fixed network capacity. So this is kind of a fair comparison because they make same assumptions about the scenario. For example, none of the methods employ replay or network growth. So here we see that NISPA outperformed all baselines, and thanks to sparsity, NISPA uses 10 times fewer parameters because it is sparse and all other networks are dense. Next, we investigate the optimal density level in which NISPA performs the best, and we found that optimal density is determined by multiple factors, including dataset, number of tasks, mode of the input. But one common pattern across different datasets is that we always want to have sparse network in order to achieve peak performance. So here I show it with pink bars, and all models perform best if we have a sparse network. So when density is too low, the model suffers from underfitting, and this is something we expect. But surprisingly, if we have more connections than needed or density is too high, we still suffer from poor performance. And my intuition about this is that some of the operations such as selection and connection rewiring or like freezing becomes very unstable if we have densely connected layers. So to sum up, sparsity is essential part of NISPA. If you take NISPA and run it on dense networks, you will see a worse performance. Finally, we analyze the effect of similarity of tasks on the number of stable and plastic units that we select. Here we have two task experiment where first task is the standard EMNIST and the second task is the permuted EMNIST. We choose this task because random permutations of EMNIST is equally challenging for multi-layer perceptron models. So only variable in this experiment is number of pixels we permute. So we have this knob where we can tweak in order to get similar tasks or different tasks. And this experimental results suggest that if tasks are similar, NISPA automatically reuses existing knowledge and it does not select many additional stable units. Or if on the other hand, if tasks are totally independent, we select large number of additional stable units. This is something we expect, and we can argue that this shows that NISPA has some kind of implicit novelty detection mechanism where it can determine whether the second task is similar to previously seen one. In conclusion, NISPA is a neuro-inspired continual learning approach. It uses sparsity and dynamic connectivity to avoid catastrophic forgetting. And thanks to sparsity, it outperforms baselines using up to 10 times fewer parameters. So I mentioned some of the limitations of NISPA throughout the talk, and in future work, we want to address some of them. So for example, brain selectively forget things, especially if they are not recalled frequently. So our brain does not have perfect memory. This is not probably a bug in our design, but it is like a feature because if we remember all the things as NISPA does through freezing, we will eventually run out of capacity. So we need to have some kind of control forgetting mechanism to recycle unrelated learning capacity that doesn't use much and use it for future tasks. So we need to come up with a mechanism that selectively unfreezes some of the stable units and put them into back like plastic unit set. Second, I mentioned that our connection growth is mostly random, and we plan to use some network theoretical metrics such as node degrees or number of input-output paths that passes through neuron to determine a smarter growing mechanism. Third, NISPA starts with a random topology and it evolves the topology in time. And this actually leads to a very interesting behavior where functionality of the network and the structure of network mutually affects each other, which is known as coevolutionary network dynamics. So we want to investigate this dynamics, and our motivation is that maybe we can come up with some network motifs that are very useful for continual learning. And finally, we know that brain also have a sparsity in activations, not in the so connection sparsity is in the structure level, but brain also have sparsity in activations, which is like functional sparsity. We want to investigate this type of sparsity as well. So thank you.
Awesome. Yeah, great. Thank you so much. That was a wonderful presentation.
Thank you.
Now we'll have some discussion and questions. So if you are joining us on YouTube Live, feel free to pop any questions or comments you have in the chat. And if you're on MS Teams, feel free to unmute and ask your question directly. I'm going to start with a quick clarification. You may have mentioned this, I'm sorry, but when doing inference with your method, do you have task maps for which neurons to use for past tasks, or do you have, or is it all just you use the same topology when after I've trained task 3, for task 1 it's going to have some forgetting or interference?
We have the same topology. We only have multi-heads and we select the head. So there is a difference in task incremental scenario. Some models assign each different mask for individual task. We do not have that. Basically, these masks are embedded in the overall topology implicitly.
That's what I thought, and that's a good strength. I just wanted to clarify because there are many some similar works that have these type of sparse connections, but they keep a task map for every past task. And another question I have before I release to others, you actually answered a question I had prepared, which was some analysis on related tasks. You showed at the end, like if it's a related task, we need fewer. So here's a question: as I guess if you were to revisit a new task, I would assume that if it was the exact same task or a very, very different data but same task, I would assume your method would either not add any new parameters or very, very, very few. Is that correct, that your method should be able to handle seeing a completely new, or sorry, the complete same task again?
Yes, actually, let me see. Okay, there is two things. First, let's say this is the task ID of one. If we are using the same head, exact same head, probably we will never like select any additional thing because we already have frozen body that connect to those heads. But let's say these same classes appear, but we are not aware that they are same with any of the previous tasks. So we will have a different head, which will connect to different subset of units. But eventually, this may lead to selecting additional units, but it will not select too many additional units.
Right, it'd be very, very, very similar, if not this. Yeah, okay. That matches what I was expecting. Thank you for your answer. There is a question on YouTube Live, and you may not know this, but at the same conference there is another paper named "Forget Free Continual Learning with Winning Subnetworks." Are you familiar with that paper?
No, unfortunately, no, but it sounds like a very similar method.
Yeah, I guess they were going to ask if you could comment on similarities, differences, but yeah,
Yeah,
same
but I
conference. That happens all the time, actually. So, yeah, maybe something to check out later and see, straight similarities, differences.
yeah, that's a good suggestion. I will take a look at the paper.
Another question was asked from somebody, not on YouTube Live, through Slack, and they asked, could you explain the why three phases to select candidate stable units? Was that a hyperparameter,
Oh,
where fewer would be worse performance and more have diminishing returns, or is there like some reason for three?
so okay, basically, the tree is for just illustration purposes,
Ah,
and basically we have like we do not fix the number of phases, but we have this kind of separate validation set where we measure the accuracy of the current task on the validation set, and we are performing early stopping in phase level. So if a phase like detrimental effect on the performance on current task, we remove that phase from and like we revert everything to back and stop. The reason is that more phases are always better because it means we are restricting the selection more. But if you restrict too much, you basically cannot learn the task. So basically, ideally, we want to have as much as phases as needed, but we can't be too generous on number of phases because it will
right.
destroy the performance for the current task.
Oh, that's the very valid machine learning practice to do. You're treating
Mhm.
it like training epochs. That makes sense, having some holdout data. Okay.
Mhm.
Yep. Makes a lot of sense. Are there any other questions on YouTube Live, or anyone on MS Teams have a question?
Hello, can you hear me?
Yes.
Hello, my name is Jair. Great presentation. I have one quick question. At the beginning, you showed that for the mammalian brain, in time, you see this high density on the early years, and then you see a decrease, and then it stays constant, right?
Mhm.
Have you seen this on your method itself? Some kind of pattern that shows you something similar to this?
Okay, the thing is that our method basically starts in this adulthood period where we have the sparse network and it is fixed, and we do not consider this type of like the evolution part of the brain. But one maybe a good idea is that starting from some kind of dense architecture and pruning it by some pre-training period. So a baby brain starts, and during pre-training you maybe like grow new connections, then prune it, and then you start with some non-trivial topology and non-trivial weights that are pre-trained. But our method does not focus on this kind of like the growth of a child period. We just start in the adulthood without any pre-training.
Okay, I see. Thank you.
No problem.
Makes sense to me. Yeah, I think there's there's a lot of discussion on pre-training now in continual learning, and I think that's like a that seems like a valid one, trying to like either that or an evolutionary algorithm try to some way motivate that we don't start from complete scratch. But I know it's very nuanced. But there has been a lot of pre-training type work is starting to be better appreciated in the continual learning community. So that is something to maybe think about future work.
Mm-hmm. But the thing is that like I think our scenarios are very simple. And for example, if we are performing CFAR 100 and we are pre-training on CFAR 10, which is like a very common practice, I think it makes the learning very much easy because our first pre-training data set actually is a very good representation of what we will see in future. Maybe real world is like this. Our world is also highly structured, but I am not too certain about whether it is like kind of cheating and easy. It makes the scenario much easier, or it is actually something we need to explore. So I am not sure whether like pre-training is good or bad, but yeah.
Let me give you a flip side of that. There's another way to view it. Is you can view it as instead of pre-training, you could view it as a large first task. So you could say, my continual learning is I do 50 or 60 tasks or classes for CFAR 100, and then I have a bunch of small tasks after that to represent, hey, we trained this model and we need to keep adding more capacity to it. So that's another way you could view it as, rather than having like pre-learning, just think of it as we tried our best on our model in this first task, but now as we're deploying out into the world, but I know that's less biologically inspired, but yeah, there's a lot of discussion, room for discussion here. But yeah, I guess
definitely there is some kind of pre-training in the brain. We do not start from scratch.
I don't know. Watson, my dog, he kind of felt like he started from scratch for sure. So we'll see there. Okay, well, there are no more questions. I guess this is a great time to wrap up. Thank you, everybody, for joining today, and thank you, Barak, for this wonderful presentation, this new flavor of continual learning. Yeah, that's great. And for the audience, join us next week at the same time and same place for the next installment in this series. We will be sticking with UTC time and not shifting for daylight savings or summertime ending. So thank you, everybody, and see you next week.